All right, we're back here on Wednesday for lecture. We're starting chapter 29 today, which is magnetism. We're going to start off with a qualitative introduction to magnetism, and then we're going to go over a quick review of a few mathematical tools that we're going to rely on heavily in this chapter, namely the cross product and this concept of unit vectors, which you've used in the course, but a review is probably good here. This is chapter 29. Got a couple good links here for the review of the cross products. Quiz 4, Monday the 12th in class, covering homework 9. Homework 11, which concerns this chapter 29, will be due Saturday the 17th at 11:59. I'm extending the due date. Unit exam 3 will be a week from Monday on the 19th in class, and it will cover chapters 27 through 29. So we'll start off with a basic review of magnetism. We won't do any math here at the beginning, just to get a qualitative understanding. So some of this you probably know if you played around with magnets, that a permanent magnet has two poles. It has what's called a north pole, and it has what's called a south pole. And if you take two north poles of a magnet to push them together, they will repel. And if you take two south poles from two magnets and you try to put them together, they will repel. But if you take a north pole of one magnet and you put it close to the south pole of another magnet, they'll attract, they'll stick together. And so these poles behave a lot like charges, and we'll see that the north poles of magnets share some common features with positive charge, electrical charges, and the south poles of magnets behave in some ways like negative charges. And so remember, positive charge, you put a positive next to a negative, they'll attract. You put two positives together, they'll repel, right? So the poles behave in some respects like charges. In fact, you'll see in a little bit that the magnetic field of a bar magnet is exactly the same as the magnetic field of a positive charge and a negative charge separated, which we called an electric dipole. So they produce identical fields. Couple differences. If you break a magnet in two, you will get two pieces, but each piece will have two poles. Okay? So in other words, you can keep breaking magnets into halves, but you can't separate the north pole and the south pole. You will continue to get another little piece that has a north and a south. By contrast, if you take an electric dipole and you, quote, break it, or we separate the positive charge and the negative, we have two monopoles. We have a positive charge and we have a negative charge. In other words, when you separate them, you don't get two pairs of positive and negative. So that's one difference, is there's no such thing as a magnetic monopole. You can keep breaking the magnet, and it'll keep breaking into a piece, each with a north pole and a south pole, albeit weaker magnetic field. We'll see in a little bit that the source of all magnetic effects are what are moving charges. So moving charges create magnetic fields, and moving charges experience magnetic forces when they move in magnetic fields produced by other charges. So we'll see shortly that electricity and magnetism are intimately related. One example of a magnet that you've probably used is what's called a compass. And all a compass is a compass is a permanent magnet, and it has a north pole pointing along the tip here, and it has a south pole which is along the side of the needle with a tail, and it's allowed to pivot. And so what the compass will do is the compass will align along the direction of the magnetic field produced either by the Earth, we'll see in a minute, or by other sources of magnetic field. The compass will point along the field. And if you take a bar magnet, we'll see in a minute that the magnetic field of a bar magnet looks like this. It looks exactly like an electric dipole. Okay, you have field lines going from the North Pole and ending at the South Pole. Okay, so they go from north to south. Okay, and since a compass will point along the magnetic field direction, we could place the compass at all points, and the compass would map out the direction of the magnetic field. So here's the field lines. These are a magnetic field of a bar magnet is just the magnetic field of a dipole. This is a magnetic dipole. And if we put the compass at every point, the compass would point along the direction of the field. I think you're going to be doing this in one of your lab exercises. We can just point at everywhere you can put the compass, in whichever direction it points is the direction of the field. And so a compass can serve as a probe for determining the magnetic field direction, just like a positive probe charge back in chapter 23 was used to determine the electric field direction at any point. So let's stop here and let's do a video.
The magnet underneath the glass dish before you sprinkle the iron filings, right, to sort of contain the mess. You can also use two wooden pieces to lift the plate off the magnet if you want to. And of course it's a glass dish, so you can project the image onto the screen with an overhead projector. Okay, so here you can see our bar magnet. Right? You want to focus the overhead projector so you get a nice crisp view of the magnet, and then take the iron filings and sprinkle them into the dish. It very nicely shows those magnetic field lines.
Okay, so the iron filings are iron. We'll see in a next lecture or two that iron is a magnetic material, and so when you crush it up into filings, each of those little filings acts like a little compass, and the filings will align along the directions of the magnetic field. So just like compasses, these filings were able to map the field. And what you saw probably is that the field is very strong near the poles of the magnet, right? And that's because the number of field lines, the density is highest near the poles, okay? Just like the electric field is strongest near the charges, the electric field lines are closest together near the positive and negative charge. The magnetic field lines produced by the bar magnet are closest near the North Pole and the South Pole. And so again, the South Pole behaves a lot like the negative charge. The North Pole behaves a lot like a positive charge. Just like the field lines went from plus charges and ended on minus charges, here the field lines go from the North Pole in toward the South Pole. One difference is that the lines form loops. They come back upon themselves inside the magnet, whereas the electric field lines ended on the negative charge. But you have a highest density of field lines near the poles, and that's why the magnetic field is the strongest near the two poles of the magnet. So the density, just like electric field lines, magnetic field lines map out the force that a moving particle would feel. And so just like we used electric field to represent electrical interactions between charges, we will use the magnetic field to describe the magnetic interactions between charges. So the magnetic field lines, this looks identical to the electric dipole field, only this is what's called a magnetic dipole. So we've said that the compass will point along the direction of the magnetic field. Okay, so if you've been out hiking and you've used a compass, you've probably observed that the compass will guide you north, right? The compass points north. Why is that? Okay, well, if you look here, the Earth's magnetic field, the Earth behaves like a bar magnet, okay? And so the Earth's field is identical to that of a bar magnet. Except if you look, there's a couple differences here. Here's the Earth's geographic North Pole, and here's the geographic South Pole, and along this line is the axis of rotation. However, the magnetic poles are about 11 degrees off from the geographic poles. And then furthermore, the north magnetic pole is really the south pole of the bar magnet. Okay, so in other words, if you look, the field lines of the Earth, remember the field lines come out of the North Pole and go toward the South Pole. Well, the Earth's magnetic North Pole is really the South Pole of the bar magnet. And so that's why the compass will point toward the north magnetic pole here. Is remember the compass, the North Pole of the compass, which is the tip, is attracted to the South Pole of the Earth's magnetic field. And so the South Pole is the north magnetic pole, so the North Pole of the compass will be attracted. It will point north because this is the south magnetic, or the north magnetic pole is actually the south pole of the bar magnet here. So the North's geographic North Pole actually corresponds to the magnetic South Pole. So that's why your compass points north when there's no other magnetic field present. So that's just a little bit of a little warm-up as far as magnetism. But to get into the quantitative study of magnetism, which we're going to do tomorrow, we need to do a little review of a couple mathematical topics here. The first you've used a little bit of, you should have, with torque. I don't know if you remember back from 1150, we said that the torque is equal to R cross F, moment arm crossed with the force. And that mathematically is a cross product. Almost all the important equations for magnetic fields and forces involve this cross product operation. It's the cross product of two vectors. So we're going to do a little review here. So suppose you have two vectors, and you have a vector A and you have a vector B. The cross product, by definition, this cross product C is A cross B, is a vector in a plane perpendicular to the plane containing A and B. And so, for example, if A and B lie in a horizontal plane, the cross product C will lie in a vertical plane. And the magnitude of this cross product is equal to the magnitude of vector A multiplied by the magnitude of vector B multiplied by the sine of the angle in between the two vectors. Okay, so if I know the magnitudes of A and B, the two vectors, and I know the angle between them, I know the magnitude of their cross product C. Okay, so the problem is getting direction. Okay, we know that C must lie in a plane perpendicular to A and B. And so if A and B are horizontal, then C must be vertical. But is C up or is C down? Okay, to determine which one it is, we have to use what's called the right-hand rule. Now, you probably use, I think you use this with torque. You should have in 1150. So to get the right-hand rule, you take your hand and you put it in the direction of A. So you put your hand in the direction of A, point your fingers in the direction of A, with your palm pointed toward B. So you point your fingers in the direction of the first vector, A, and you have your palm facing the second vector, B. And your right hand, that's why it's called the right-hand rule. So you take your right hand, point your fingers along A, your palm pointing B, and you curl your finger. And your thumb will give the direction of C. Okay? So in this case, your fingers are pointing along A with your palm toward B, and you curl your fingers, and your thumb points upward, and so C is pointing perpendicular to A and B, pointing upward. Okay. And its magnitude is equal to the magnitude of A times the magnitude of B times the sine of the angle in between. Okay. So what that means, since sine is biggest when alpha is 90 degrees, it means that the magnitude of the cross product is greatest when two vectors are perpendicular, angles 90, and the cross product is 0 if the two vectors are parallel, because sine of 0 is 0, or if they're anti-parallel, because sine of 180 is 0. So the cross product is maximum when they're perpendicular, and its direction is given by the right-hand rule. Okay, now one thing that we probably haven't noticed yet is that the cross product is not commutative. So regular multiplication is commutative, right? If A times B is B times A. Well, the cross product isn't. If you take the vectors and you operate on them in the other direction, you get the negative. And we can see that by the right-hand rule. Okay, you get the same magnitude for both, but the direction is opposite. Okay, so here is A cross B. So again, you take your fingers and you point them along A with your palm toward B. And you curl your finger and your thumb points upward. Okay, now what if we did B cross A? Okay, well, here we have to point our fingers along B, but the palm has to be toward A. So you have to put them, your hand has to be the opposite, right? Fingers along B, palm pointing toward A, and then you curl your fingers from B toward A, your thumb points downward, okay? That's the opposite direction is A cross B. So if A cross B points upward, B cross A will point downward. They'll still have the same magnitude because they still have the same angle between, and they both have the same magnitudes of A and B, but the direction will be flipped. So make sure to remember that when you're doing the cross product, is it's not commutative. Okay. Now, that's one way how to calculate the cross product, is if you know the magnitude of the two vectors, and if you know the angle between them, we can use A times B times the sine of the angle. That gives the magnitude, and we use the right-hand rule to get the direction. Okay, now there's going to be times coming up in the chapter where we will not have the magnitude and the directions of both, but will be given the three components in the x, y, and z directions for the two vectors. And so there's another way that we can calculate the cross product if we know the components, but we don't know the magnitudes. And in this case, we use what's called a determinant. And if you've taken linear algebra, you probably know what a determinant is. And if you haven't, don't worry. Just use the formula that we're going to use here. So if you have a vector A, and A has components AX along the I direction, and AY is along the J direction, and AZ is along the K direction, and then you have another vector B which has a component BX along I, a component by along j and a component bz along k, the cross product is by definition the determinant of this matrix. And so to get the determinant, okay, if you don't know this, just use the result. To get the I component, I is up here, it's element row 1, column 1. We cross out row 1, we cross out column 1, and then we take the diagonals of what's left. Okay, so it's AY times BZ minus the other diagonal, AZ times BY, and that's the I component. Okay, for the J component, which is here, we cross out the second row, second column in the first row, and we use AZ times BX minus AX times BZ. Then for the K component, we cross out the column in the row K is in, so we cross out column 3, we cross out row 1, and we take the diagonal, it's AX times BY minus AY times BX. And if that was a little difficult, if you haven't taken linear algebra and haven't done determinants, just write this formula down and use it on the cheat sheet for your exam and your homework. There's another way to get the same result, and this may be a little easier if you haven't taken linear algebra. There's a little trick here. So if you have two vectors, A and B, and they each have AX as the I component, Y as the J component, and AZ as the K component, we write the unit vectors twice. So we write I hat, which is the unit vector along I, J hat, K hat, I hat, J hat, K hat. Then we write the three components of A twice as well. AX, AY, AZ, AX, AY, AZ, BX, BY, BZ, BX, BY, BZ. Okay? To get the I component, we take the diagonal, we shift one to the right, and it's AY, BZ minus AZ, BY. To get the J component, we go one over and we do the diagonal, AZ, BX minus AX, BZ. To get the K component, we go one over, so we point this, it's AX, BY minus AY, BX. So that's another way to remember it if you haven't done linear algebra and determinants, is you write each one of these twice, and then we take the diagonals between the two. So let's do an example here. Suppose the first vector A is 5I plus 3J. So in other words, its X component is 5, its Y component is 3. And we're going to take the cross product with another vector, which is negative 2I minus 3K. So its X component is negative 2, and its Z component is negative 3. Okay? So we can write IJK, IJK, and then vector A, its X component is 5, its Y component is 3, its Z component is 0. So 5, 3, 0, 5, 3, 0. The second vector, B, X component is negative 2. There is no Y component, so 0. The Z component is negative 3. So its coordinates are negative 2, 0, negative 3. We write that twice. Okay. Then we do our diagonals. So the I component, we move over one row and we do it. So it's 3 times negative 3 minus 0 times 0. The J component is 0 times negative 2 minus 5 times a negative 3. The K component, we go over 1 and we do the diagonal, 5 times 0, this diagonal, minus 3 times a negative 2. And then we add them all up, and the result is negative 9I plus 15J plus 6K. So the result has components along the X direction, the Y direction, and the Z direction. Okay, let's do one more example. Suppose your first vector, suppose this is call it vector P, and suppose its coordinates are 2, -3, and 1. So 2 along the I direction, -3 along the J direction, 1 along the K direction. Then here you have the second vector, which has 4 along the I direction, -1 along J, 5 along K. You can write it as a determinant, or we can use our cookbook here. Okay, so AY, which is what? The first vector's Y is -3. The second vector's Z is 5, minus AZ, which is 1, times BY, which is a -1. Then for the J component, it's -2 times 5 minus 1 times 4, or we can just do this. AZ, it's plus AZ, which is 1, times BX, which is 4, and then minus AX, which is 2, times BZ, which is 5, and that's just the opposite of this. You get the same result, and then so on, and you get -14I minus 6J plus 10K. So work on a couple of these examples and take a look at this cross product tutorial. It only takes 5 minutes to read. Stop by office hours if you have any questions about that. So now let's look at unit vectors. Okay, we've talked about these I hat, which is the unit vector, a vector of magnitude 1 along the x direction, and j hat, which is a unit vector 1 along the y direction, and k hat, which is a unit 1 along the z direction. Okay, these are called unit vectors. They have a magnitude of 1, they're along a given direction, and their main purpose is to break a vector down into the components along the 3 directions. So I hat is just nomenclature for meaning the vector is along the I direction. So what we want to do is get some relationships. So we know between these unit vectors. So we know that the cross product, the magnitude of the cross product is the magnitude of the first times the magnitude of the second times the sine of the angle between. Now for all of these vectors, since they're unit vectors, the magnitude of A and B are each 1. So if we do I hat cross I hat, the magnitude is 1 times 1 times the sine of the angle between them, which is 0, is equal to 0. So the cross product of I hat, the unit vector with itself, or any of the unit vectors, is 0. Okay. Now let's do the cross product of the unit vector I hat with j hat. So the vector magnitude 1 along x crossed with the magnitude 1 along y. Well, the magnitude is 1 times 1 times sine of 90, which is 1. So the magnitude of the cross product is 1. Okay? The direction is given by the right-hand rule. You take your fingers and you point them along the x direction with your palm along the y direction, and you curl your fingers from x to y, and your thumb points along the plus z direction, which is k. So I cross j is k. Okay? You can do the same thing here. You take a unit vector along the y, and you cross it with a unit vector along the z direction, so j hat cross k hat. Again, you have a magnitude of 1, and it will point along the plus x direction, which is the I hat direction. Okay? And so you can go on and you can get relationships between these unit vectors. This stuff we're going to be using later on when your vectors are in terms of components. Now, if you have your unit vector along some arbitrary direction that's not the x direction the y direction of the z, but some arbitrary direction r, we'll often need to calculate this unit vector. And to do that, the unit vector r hat along some direction defined by r is just the vector r divided by its magnitude. So here's an example. Suppose you have a vector A, and it has a component, it's 1 along the I direction, plus 1 along the J direction, plus 2 along the K direction. Okay? And we want to make this into a unit vector which points along this same direction but has a magnitude of 1. Okay? To do that, we just take each component, each of these, and divide by its magnitude. And to get the magnitude, we use Pythagorean's theorem. 1 squared plus 1 squared plus 2 squared is the square root of 1 plus 1 is 2. 2 plus 4 is 6. So the magnitude of this vector is the square root of 6. So all we do to get the unit vector A is just divide each component by the square root of 6. So it would be 1 divided by the square root of 6 I hat plus 1 divided by the square root of 6 along J plus 2 over the square root of 6K. So that's a review of unit vectors. So tomorrow we're going to start to apply some of this math toward calculating magnetic fields and magnetic forces. So I encourage you to look at the tutorial, brush up on your cross products and on your unit vectors. We're going to come back tomorrow and we're going to use them. So have a good day.